Okay. Sorry for the delay. I was busy preparing my talk. I was advised, we were all advised, all the speakers, to choose something that would be easy to understand for students. And I'm not sure this is going to be easy to understand, but I hope so. And I wanted to talk about how I, in my career, chose science problems, which is probably the most important thing any scientist will have to do in their careers, is actually to decide what they're going to work on. And so the theme of this is that you think that science proceeds with a grand vision, or maybe your career might proceed with a long-term vision of what you want to do. And then you just execute this plan, but that's not really what happens. Sometimes things happen by accident. Let me give you an example. This is my father and my mother getting married. My father looking at his oldest sister. My father was a professor of chemical engineering. My mother and father came to the United States during World War II to go to MIT to graduate school. And by then, my aunt, was a professor in Tsinghua University in chemistry, a full professor. And you'd think that with good-looking parents like that, they could produce something like this. And so this is, something falling pretty far from the tree. On my mother's side, now she studied economics in graduate school, but she started to raise a family and dropped out. But her father and her uncle were also very distinguished. There's my grandfather and granduncle, a photo taken in New York City. And my grandfather, who was born in 1900, went to the United States to get a degree in civil engineering. At Cornell, he comes back, he becomes a professor. In those days, you're sent abroad if you do very well in exams. It's kind of like Singapore. And they bring you back and you can get some good position. So he began as a professor at Pyongyang University in 1926. But by 1932, he became the president of the university. And he remained there until the Communist Revolution in 1949, and he had to flee for his life. So he came to the United States. Now, my granduncle, I didn't know this until I was an adult in my 30s, but he actually was a physicist. He was born 10 years earlier than his brother, and he earned his Doctor of Science with Jean Perrin. Now, Perrin is the person who studied Brownian motion following a suggestion by Einstein. And in measuring Brownian motion, you could actually find Avogadro's number, and hence you can actually weigh an atom, so to speak, because 1 mole weighs so many grams. And Perrin gets a Nobel Prize for this. The same year he gets a Nobel Prize, my granduncle gets a big medal from France. Why? Because he was the graduate student who did the experiment. So I said, wow. So you think, okay, with such a distinguished family and good genes, how can I go wrong? Easy. I thought when I was growing up that I was truly the academic black sheep of the extended family. So let me tell you why. I had an older brother. He went to Princeton, then went to MIT, got a PhD in theoretical physics at MIT, did a postdoc at Berkeley the same year I was starting there. And he realized, well, he's not going to get a faculty position at one of the top half dozen universities in the United States. So he said, well, maybe I'll do something else. So he goes and gets an MD, PhD in biochemistry. And now he's a professor of oncology and biochemistry at Stanford. Okay, now growing up with this older brother who not only was a valedictorian, he set the highest cumulative average ever in the history of the high school. I come along and say, oh, we expect you to do just as well. It's going to be really neat. And so I dropped out of high school in 9th grade for 3 months. Eventually decided I better go back. My younger brother had even rougher time of it because you grow up in an Asian family. And you know what Asian families do? They say, look at your brother and how successful he is. What's wrong with you? You're laughing, you know this. And in any case, My younger brother had a falling out with the parents. He dropped out of high school, didn't graduate his senior year, bummed around for a year, and finally decided on his own, well, maybe I should do something. Maybe I should go to college. But he didn't have a high school diploma or the blessing of the high school. So he talked his way into UCLA because he charmed a professor or two. But he managed, while he was an undergraduate, he got into the big poker game. The big poker game was where the president and the provost were playing poker with other faculty members, and one undergraduate, my brother, he got a PhD at the age of 21 to stay out of the draft. And then he went to Yale Law School with a young lady he married. They got disowned. My sister-in-law's parents disowned her for marrying a ne'er-do-well, my younger brother, because they thought he was going to be a bum. He'd go to Tijuana and do crazy things. My younger brother introduced me to marijuana. That's how. But he did okay. He got a degree from Harvard, and he's now one of he's currently a patent litigator. He's one of the most famous patent litigators in the United States ever since he was in his late 30s, and he's also one of the most expensive patent litigators. And he has done other things, like he was president of the board of overseers at Harvard. So you got to understand, my brother goes to Harvard, my two male cousins go to Harvard, my younger brother goes to Harvard. I never went to Harvard, never had a degree, and only by luck they gave me an honorary degree, and I said proudly, at last I can hold my head up in front of my mother. So this was a terrible family to grow up in. And I truly did feel like I was a family failure. I got rejected at Princeton and Yale. I went to Rochester, and it was the best thing that ever happened to me because they never heard of my older brother. But because of that, I actually got a lot of special attention in the math and physics departments. And math you can advance pretty rapidly. I was not a serious student until senior year, but I became a serious student. It was like my younger brother. And so I was invited to the faculty parties in the math department beginning my junior year, but they didn't invite the graduate students, just like my younger brother getting the big poker game. So anyway, so I go to Berkeley thinking, oh, I went to Rochester. I'm not going to do well with all the brilliant people from Harvard and MIT and Caltech. And I was relieved after the first quarter because these people were asking me how to do their homework problems. So that said, okay, I got a good education at Rochester. Now, I learned something really important at Berkeley. And the lesson I learned at Berkeley, by looking at some of the very successful scientists, they had 7 or 8 Nobel laureates active at the time at Berkeley. And the lesson I learned is if you build a new instrument and you can see something new, you don't have to be smart. I was convinced I wasn't smart, so I said, well, if I can help build something new, and the thing I tell my graduate students, if you're the 100th person to look under a rock, you have to be really smart to find something new. If you're the first person to look under the rock, or you can look under the rock with a new set of eyes, you don't have to be smart. You just have to keep your eyes open. And so at the time, in the 70s, I started as a graduate student in 1970, the tunable dye laser was invented in 71 or 2. And I told my advisor, Eugene Cummins, who I wanted because he was he was the most famous physics teacher at Berkeley. And so I really admired that. And so he asked me to join his group of 1. I was for a while a sole graduate student. He had a very small group and the others had just left. And I said to him, I want to work on dye lasers. He says to me, I don't know about lasers. I don't know anything about lasers. He says, don't worry, I'll learn about lasers, I'll teach you. Then we had to hunt for an experiment to do. So we hunted around for an experiment. And finally, we didn't find it. It was given to us by Marion Marie Bouchard and her husband, and that was you can do a laboratory experiment using lasers to test a very fundamental theory that was unifying the weak and electromagnetic interactions. Now, I don't have time to tell you much about what that means, except the weak interactions are responsible for beta decay, a very, very weak force. The electromagnetic interactions, 14 orders of magnitude stronger, electricity and magnetism, which you all know about. And it was very unlikely that it was possible that these had any connection, but Weinberg, Salam, and Glasgow found that they were deeply connected. And this unification of the weak and electromagnetic interactions led to a prediction that there must be a new particle in the weak interactions that was a neutral particle. And so if you think of an atomic atom and the interaction of the nucleus, the protons, the charged particles with the electrons, it's mediated by a photon, a neutral boson. With the new theory of weak interactions, there was a new boson that's neutral that could also interact. And therefore, since weak interactions didn't conserve a parity symmetry means you have your right hand, you look in the mirror, it looks like a left hand. If you build a watch that is the mirror image exactly and all the screws go clockwise instead of counterclockwise, vice versa, the watch keeps perfect time going backwards and all the numbers look backwards, so the mirror image works. So that's called parity symmetry. Weak interactions don't support parity. And so the idea in a nutshell was if you take an atom, there's no external field, and you come in and you have circularly polarized light. That is light with an oscillating electric field that goes around in a circle. If you're looking at a plane and linearly polarized light, the electric field goes up and down. If you're looking at this plane and look at in a circularly polarized light, the electric field goes around in a circle. If you come in with these right and left-handed light, the prediction was the absorption should be different. Very small difference. If you come in with a very, very forbidden transition that goes mostly magnetic dipole, I'm using technical words, I'm sorry, I'll start all over again. You just work on this and you make the effect as big as possible, and it's about a millionth of a difference in the absorption of the very weak optical transition. In fact, it was so weak, no one has actually induced such a weak optical transition in the past. So that was my thesis. It was hard. We were poor. I had to make my own lasers. It was worse than that. I had to scrounge the power supply from a Livermore junkyard. I literally had to make the laser myself and all the pieces. And so there's me adjusting this laser I made. And so this is my advisor, Eugene Cummins. This is with my mother. It's at the Nobel Prize ceremony. My mother's telling my advisor how Stephen never listened to her ever. But let me say that one of the things my advisor said to me was, he said, look, you're pretty good. You're very good. You shouldn't work on anything less than the most important problems in physics. And when the most important problems are the most fundamental. Things that really test the fundamental symmetries of nature, things like that. And so that was what I was told. For whatever reason, so I was a graduate student there, a 6-year graduate student. I had 3 or 4 failed wandering experiments and finally landed on this experiment. So I was, my father was kind of worried. He said, I took 2 years to get my PhD. Why are you taking 6? And why aren't you in the, by the time I was 43 or 2, he said, why aren't you in the National Academy of Sciences yet? I was. Anyway, it's terrible. So for whatever reason, they asked me to apply as an assistant professor at Berkeley. So it was the one school I did apply to for an assistant professor job. Those were good old days, you could say. You apply to one school and they take you. But they took me. I don't know really why. They gave me a set of funds to say you can start your own group. I had a very narrow view of science, so I thought of a better way of doing the experiment. And, but people at Berkeley also said, since I grew up doing this one experiment as a graduate student and postdoc, you have a narrow view of the world. You can start your group now, or you can go away and take a leave of absence for a year or two and come back. The job is yours. So I said, that's great. I took the money, I spent it on this laser. Started grooming my first graduate student and went off to Bell Labs. And the graduate student would visit me at Bell Labs, and we built this laser apparatus. So there I was at Bell Labs, which is an eye-opening experience because the faculty at Berkeley were right. I had a very narrow view of what was going on in the world. Just to give you a sense of Bell Laboratories, there were 15 scientists who worked at Bell Labs that got Nobel Prizes, but they were all recruited not as big shots who have already done the work. They were all recruited as young scientists at the beginning of their career. And so it was a spectacular place. And when I went to Bell Labs, I started working on fundamental things like Anderson localization, Mott transition, phase transitions in condensed matter physics. I used lasers to excite a very exotic atom consisting of an electron and a positron called positronium. That made a very big splash, but it was technically hard. People had trying to do it for 20 years and failed, but it led to nothing new. And so even though it was a big splash, it gave you street cred, but it didn't lead to anything new. This is what I looked like, by the way, when I was at Bell Labs. And then I said, I met a guy named Art Ashkin, and he was trying to trap atoms since the early 1970s. I moved to Homedale in 1983. And he was trying to get me interested in it. Management had shut down that effort about 6 years before that because they were not making progress. I studied it. Yeah, they were right, not making progress. But I kind of stumbled independently on something that's called Doppler cooling. So how many here know about laser cooling at all? Please raise your hands. Yes, so I'm going to skip it. No, I'll do it. Here's an atom, and it's surrounded by two laser beams, and it's using the Doppler shift. So this is the resonance absorption of the atom. If the atom is going towards this laser beam, it sees not the frequency of the laser, but a Doppler shifted frequency up. So it's tuned more in resonance. It scatters more photons. When it scatters the photon, it gets momentum impulses, slow it up. It's running away from this laser beam, so it's tuned out of resonance. So even though it's scattered from both laser beams, it's scattering more light from this one than that one. And so the net effect is it slows the atom up. And in fact, you can easily generalize this 3 dimensions. You just have beams coming this way, and that way. And I independently discovered this. I have a habit of not reading the literature. It's a bad habit, maybe induced by being a poor student. But actually, it's a good habit because I'd rather try to figure it out on my own if I have a hint of what has happened. Anyway, when I did the experiment, I sat down to write the paper. Ashton said, you should read this paper by Shallow and Hench. It might have something to do with what you did. I read their paper. My heart dropped. It was exactly that. Surround the atoms with light. Use the Doppler shift, you can cool light. It was a 2-page paper, a 2.5-page paper written in 1975. This experiment was done in 1985. It took 10 months to do the experiment from the time I had the idea to get a vacuum chamber to do the experiment. Why didn't these guys do it? They missed one calculation. They were right, it would cool atoms. They estimated it would be comparable to the line width. It wasn't important. It turned out to be far colder than that. The most important thing was I said, well, how long would these atoms, once cold, how long would they keep in this place? And I sat to write a program and said, no, I've seen this problem before. It's Brownian motion in viscous medium. And the fluctuations make it jiggle around and the viscous drag, and Einstein figured it out. So I plugged in his equation and said, my gosh, these atoms will hang around for a fraction of a second. So it'll be easy to see. And that stupid little calculation said, oh, this is going to be easy. So that one simple calculation was what it really needed. But it took 10 years. Okay, so I did laser cooling and trapping. We got optical traps of various kinds. I decided I was going to go to university. Going all the Bell Labs is a little bit hard because there's all these young whippersnappers that are coming behind you. And I had more interest, so I wanted to do other things. So I went to Stanford, and so I showed up at Stanford at age 40. This is what I looked like at age 40. And when I was at Stanford, we had these cold atoms. And you turn off the light, and they were so cold, they would drop like rocks to the bottom of the vacuum chamber. So I said, hey, that's neat. And the one application I knew about cold atoms is you can push them upward. And if you push them up, they can go up, turn around due to gravity, and come back down. And I knew of an experiment that had been tried in the 1950s, but never published, by a professor named Zacharias. And he was this poor graduate student who said, he said, put an atomic beam, the beam of atoms will go up, they come back down. You have a very long measurement time, and you can make a very precise measurement of frequency, and hence a better atomic clock. And the grad student tried, and he failed, and he found out that the fast atoms just kicked the slow atoms out of the way. So he struggled for a long, long time. And finally, after many years, he got another type of PhD. His name's Ray Weiss, by the way. He did okay. Ray Weiss got the Nobel Prize for gravity wave detection. But that was his abortive thesis project. But it was never talked about until Ray Weiss's Nobel Prize essay of his biography. But everybody knew about this. And so with cold atoms, it's easy. You have the cold atoms, you push them up into a microwave region, they come down, they do wonderful things. Now, as the atoms are going up, I said to myself, you're coming with two light beams, they're ground states, and there's an excited state. Think of a transition to a virtual excited state, virtually absorbing a photon coming from the right, and then stimulating coming down from the left. But when you stimulate coming down from the left, you get a recoil in the same direction. So by inducing a transition from one ground state to another ground state, you give it two hits of momentum. And I said, amazing. That means you can actually make the atom into a linear superposition of two states, one with a certain velocity and another with another velocity. And so here's an atom. Heuristically, you have these two protons. If the probability is 50%, it goes into this other state. In quantum mechanics, it says, no, it's in both of these states. So it's in a linear superposition of these two states, and you can quickly make an atom interferometer. And so we did this. It took a few months. And instantly, we were able to measure phase shifts in the first experiment, part in a million. Next year, part in 10 to the 8. Now people are measuring phase shifts, part in 10 to the 12, 13, 14. So it became instantly one of the most sensitive measurement methods we have today, along with time measurements. But when I was getting to Stanford, I said, well, look, we can hold on to atoms. Art Ashton discovered he can hold on to little microscopic things like E. coli, and he can take the E. coli and move them around, and they're swimming around, and he'd move them from here to there, turn off the light, and they'd wiggle around. If you turned up the light, he would opticute them. They would explode. You couldn't do that in a university. It's animal cruelty. But I thought if you could hold on to E. coli, and you can hold on to atoms, could you hold on to individual molecules? So when I got to Stanford, I got an MD PhD student who said, teach me a little biochemistry so I can glue a little polystyrene sphere, a little handle, onto a molecule of DNA. And we can stick it in an optical microscope. You could put fluorescent dyes on the DNA. You can maybe watch it. And so this is an example of DNA in an optical microscope. We hooked up motorized mirrors onto a joystick, and you can play video games with a single molecule. And so, we started doing this, and very quickly we said, this is something really funny about these DNA molecules. If you stretch it out and let it go, it collapses. It strings back like a rubber band. I said, that's amazing. Why is it doing that? Because I didn't know anything about polymer physics. And the reason it's doing that is this polymer can have many, many possible states. A very unlikely state, it's all stretched out. A much more likely state, it's all curled up. There are many configurations of all curled up. So it's just entropy that says I'd rather be up in an all curled up state. So that's what happened. It led to a whole raft of experiments in polymer physics. But I also wanted to do biology and look at some fundamental aspects of biology using these single molecules. I started doing this, and so off I was doing biology, and by the middle 90s, the majority of my work was in biology. Now, throughout this whole time, I was reminded of something I read when I was a graduate student by Erwin Schrödinger, and he gave a series of lectures in Dublin, Ireland, and in those lectures, which he calls What is Life, he said, from all that we've learned of the structure of living matter, we must be prepared to find it working in a manner that cannot be reduced to ordinary laws of physics, not because there's any new force, but because the construction is different from anything we've yet tested in the physical laboratory. He said this in 1944, it was published in 1944. And what was different about this? Well, if Newton were the size of bacteria but had the brain of Newton, his laws of motion would be very different. An object in motion quickly comes to rest. There is no inertia at the nanoscale, or even micron scale. And in addition to that, there's Brownian motion. It's fluctuating all the time. And the law of motion is not F equals ma. It maintains a steady velocity unless you have a force. If you stop the force, it stops. So it's F equals mv, where the proportionality constant is Stokes drag. And so the laws of physics in organisms is very different than laws of physics in macroscopic machines, where you have inertia and you try to make it as frictionless as possible. And so life has got to figure out how to make stuff work in this really crazy environment of highly dissipative and lots of Brownian motion. And so as I started to do this, I was led to the realization that perhaps these models and cartoons of things that molecular biologists show, you've seen these things of molecular motors, and you say it looks like this, right? No, can't be that way. It's jiggling around. And so in a slightly more abstract view, these are two legs of a molecular motor called dynein, and they're stepping around, and they're looking for a new place to walk. They set them down, they walk, they set. Okay. Now I'm only going to talk about, we started studying this motor about 5 years ago, and with, again, why were we studying it? Because we had a new probe. We had much better time and spatial resolution. We could measure in a live cell for many, many tens of minutes the movement of a cargo in a live neuron without killing the neuron. And we discovered through this, looking at this for a long time, that the model was wrong. It uses 2 ATP, not 1 ATP. That's a horrible place to be, because if you think the accepted model is wrong, it takes a few more years to get things published. But one of the things that I want to stress is the molecular motor people always talk about a so-called power stroke. And in this motor, with this, these are the legs, and this purple thing here, they have it goes into a cock position, and what they call a power stroke, somehow there's a force that forces this part to come down and drag the vesicle forward. So I asked the dynein motor experts, well, where's this power stroke come from? I said, we don't know exactly where it is, but we're pretty sure it's there. But then as a physicist, I say, well, suppose there is a power stroke, and it goes like this, suddenly pulls it down. You can model this connected to this cargo with a spring. And so if you connect it to a spring and you suddenly move it, the position, it's a differential equation. The spring force, Kx, is equal to minus the Stokes drag force. And that's an easy equation to solve, a differential equation to solve. And you find that the time it takes to relax to the new position should be independent of the size of the step. And that's one interpretation, but if you say it's Brownian motion, and in order to actually come down here, you're doing a Brownian motion that gets it into here and that allows it to dock in place. So in this cartoon, I have it going like this. This is a small step, this is a big step. In a big step, if you think that linker is going to bring down, it's going to go, it has to diffuse a longer distance, that tells you right away if it's driven by Brownian motion, the step size has to be, the time it's moving the vesicle should be dependent on its step size, at least as the step size squared. So it's a quantitative differentiation between a power stroke and something driven by Brownian motion. And it's a very simple test. And that's the great thing about science. You have a model. Is it this or this? Can I do an experiment to differentiate between the two models? Which means you not only have to see its step, but during the step, you have to see it move. Which means, it takes a few milliseconds in between steps, but the time it takes a step is less than a millisecond. That we knew from our own measurements. We had 4 nanometer resolution, 1 millisecond time resolution. So we are now building an apparatus that's just been built. It's looking at the system. And instead of 1 millisecond, we have 5 to 10 microsecond time resolution. And instead of 1 nanometer, we have about 0.2 nanometers. And for those of you who know, and we can do this in a live cell for an indefinite amount of time. So it's a new instrument again. And so, and what we're seeing is little puzzles. So, which is kind of cool, because we've just made yet another instrument to test the prediction, but in so doing, I think we're going to stumble on other things. Okay, anyway, oops, I'm over time. Give me 3 more minutes. I'm going to tell you a little bit about climate change. The climate's changing. We're at 1.6 degrees already, so the 1.5 degree UN goal is passed. We're going to be over 2 degrees. I think we're going to end up at maybe 3 degrees. And because of my concern about climate change, I became director of LBNL, and I was thinking I was going to step down after a couple more years, about 5 or 6 years, go back to doing science. I got this strange phone call from the president-elect in November of 2008. And the bottom line is Obama wanted me to be the Secretary of Energy. I met him for an hour. I liked him, he liked me. So he's offered, I accepted. And I got a little waylaid. I had to put out some Gulf fires, things like that. But let me tell you about, I'm going to skip all that. And I'm going to tell you about something very much on my mind. We're going to need to capture carbon dioxide, not only from cement and steel and coal plants and other things, but also from the air. I think we're going to go well over 450 parts per million, probably over 550 parts per million. The trouble with capturing carbon dioxide in the atmosphere is it's very expensive, and it requires a lot of energy, and it requires a lot of capital expense. This is the size of a carbon capture tower that I funded when I was Secretary of Energy. It cost $1 billion. It was the first carbon capture plant that came on budget. It's big. That's the size of a pickup truck, and it's capturing 1/4 of the carbon dioxide from one coal plant for $1 billion. And it requires a lot of energy. And so even then, I was thinking, this is not going to be deployed, or any technology like this is not going to be deployed. And the fundamental reason is that when you capture carbon dioxide, you have to decrease the amount of energy you need to release it. You capture it from the atmosphere of flue gas, you release it at some pressure, and you pump it underground. So I'm going to tell you about a work of a postdoc of mine who did this work. And we had this stupid idea. You have a molecule. This is the name of the molecule, called tempo. Don't ask me even how to pronounce this. And it has both a reduced form and an oxidized state. Now, I have to tell you, 6 years ago, I did not know what reduction and oxidation meant. So I had to go on Khan Academy and learn the acronym OIL RIG. Oxidation induces loss, reduction induces gain. And so that was me learning about chemistry in my old age. And we thought naively that if we put an amine on this and the carbon dioxide captures the amine, if we can use electrochemistry to just break the chemical bond, we're not doing any overhead of heating up anything else. So it worked. Let me say, so we had this. We oxidize and put it in this oxidized state, and out popped carbon dioxide miraculously. We saturate some solution water with basic water, high pH water. We turn on the current, out pops carbon dioxide. So that's cool. So we do the next thing, you do mass spec, because you want to see carbon dioxide on this molecule. No carbon dioxide in the molecule. Okay, what's going on? Get rid of the amine. Just put a hydroxy group on. Same effect. Captures and releases carbon dioxide, but it couldn't have anything to do with the amine. Okay, what's going on? What's going on is then we said, well, what's happening to the pH? And as you change, if you have this molecule, and it can be, it's very soluble. It can be up to a fraction of a mole of this molecule in water. And if you oxidize it, turn it into its charged state, as you increase the oxidation from 0 to 100%, the pH plunges. We know when the pH goes down, the solubility of carbon in water changes. This was known. And in fact, it's well known that if you have carbon dioxide in your gas and it goes into water, it forms neutral carbonic acid, but breaks into bicarbonates and carbonates. And as you increase the pH, as solubility increases, if you go from pH of 11 to 5 or 6, the pH changes by, the solubility changes by more than 4 orders of magnitude. And so that was known, and because that was known, people were saying, could we change the pH of the water electrochemically, and therefore you capture in very base conditions, and you change pH, make it acidic, and voila, you release carbon dioxide. That was the idea. So here's the problem. When you change pH from high pH, that means low proton concentration. When you go from low concentration to high concentration, you're fighting entropy. Entropy wants to go from high concentration to low concentration. So the second law of thermodynamics tells you by changing proton concentration, there's a minimum second law energy you have to pay for just the concentration. Change pH by 7.5, the voltage you need per molecule, the electron volts you need per molecule is almost half a volt. And we were finding that we can use less than 0.02 volts. And yet we were changing the pH. So you might ask, so the idea is, okay, you saturate the water with carbon dioxide, you oxidize it, you turn it to a charged state, the pH magically changes, out pops the carbon dioxide, it takes energy to grab the electron, but on the return path, here's a charged, stable radical, it wants to grab an electron back. If the transition from oxidation reduction is pH independent, you gain back the energy completely. And you can show analytically, besides resistive losses of ions going through this membrane, there is no net energy, okay? So, but the question is, that's just summarizing what I just said about minimum entropy. So how can you change the pH without changing the proton concentration? And the answer is, there's a fudge factor called an activity factor. And we accidentally discovered we can change the activity factor by 7 orders of magnitude. So what was going on? What's going on, we believe, is when this is in its oxidized or charged state, you're polarizing water molecules. Oxygen is slightly negative, protons are slightly positive. Suppose you have a reaction that grabs up bicarbonate and for its neutral carbonic acid, finally CO2 and water. Then you have a deficit of protons, and this polarized molecule was willing to donate a proton on demand when you need another proton. And so it keeps the proton, this concentration to the same. It doesn't increase the proton concentration. You don't want to do that, but you pay an entropy price. But if you find something that buffers the proton concentration, keeps it the same, you pay no entropy price. And to show that, we took these charged molecules in water at reasonably high concentration, and we threw in KOH. And the OH will gobble up a proton. When it gobbles up a proton, you'd think that the pH would go from, alkaline conditions, base conditions, acid conditions, commensurate with the amount of OH you put in. But in fact, what happens, the pH remains roughly the same until a concentration where if you have a number of molecules of this oxidized proton, remember, you've got one polarized molecule. Once you rip a proton off that OH sticks on that molecule. There's no more polarized molecules, no more protons that particular molecule can give. And so it stops buffering when the number of OHs equals the number of molecules that are in the charged state. And so it was pure luck. We weren't looking for this. People probably were stumbling on it for years, but it costs no energy. And we think it's going to cost an order of magnitude or 2 less in energy if you engineer it right. It's already a factor of 20 less, and probably another factor of 5, which means the energy you need to capture goes way down. The most amazing thing is it's a very benign room temperature conditions, so you can use a trick of nature, an enzyme that captures carbon, helps carbon dioxide go into fluid like blood, called carbonic anhydrase, that increases the rate far more. And so it looks as though the cost of capturing carbon dioxide plummets by at least an order of magnitude, is my guess. And so it may make carbon dioxide capture feasible. Really doubly exciting is you can mine hydrogen by pumping hot water into iron down below in the Fe2+ state to make it Fe+, and out pops hydrogen. So you get cheap hydrogen you can mine, you get cheap carbon dioxide, and you have a small nuclear reactor. And I was talking with the guys at Breakthrough Energy Ventures, and our tune says, if you have all these things at these prices, you can make jet fuel competitive with the fuel we sell today. So it's very, very cool. So in closing, I just want to say life is like an E. coli. Why is it like an E. coli? E. coli has this rotary motor, and it can go this way, and it creates the flagella go in a spiral, it propels through water. It goes the other way, they splay out, and it tumbles. And so when E. coli are looking at food, they keep on going. But when there's no gradient of food, they don't just sit there and look bewildered, they still keep going. But when they smell food by looking at the grain, they go towards food. And so it's a kind of a funny random walk that's stimulated by some other purpose like looking at food. And so it's kind of a quasi-random walk, and that's what my career has been like. Thank you.
Thank you, Prof. Chu. May we now invite Prof. Wikowski up on stage to moderate the session, please.
Thank you very much, Professor Chu, for this very inspiring talk. And I have the idea that you don't like to be in your zone of comfort, and you would like to change a lot of topics. And that's fantastic. You did it's very successful. So maybe the session is open. So please ask your question.
Thank you, sir, for such a great talk. It was really inspirational. I just have a question. You talked about laser cooling. So I'm just curious to know about the applications of laser cooling.
Yeah, well, first, you can use it to create Bose condensates. And that's a long sought-after goal of dilute Bose gas condensing. You can use it to hold on to atoms and put the atoms in standing wave lattices that begin to test many body physics effects. And you can look at phase transitions like Mott transitions. So these are things people have done. It's now being used. A former student and a postdoc of mine have started a company to use it for perhaps a quantum computing machine. So you have a big array of atoms. You put the light through a spatial light modulator. You can pick up atoms, move them around to other atoms. You put them in Rydberg states, make quantum coherences, move them around. And so it's one of the possible ways of doing quantum computing. It makes the world's most accurate atomic clocks are using cold atom fountain clocks. The most accurate way of sensing gravity, testing the equivalence principle, and now looking for gravity waves, not yet demonstrated, could be using cold atoms. in atom interferometers. So it's got bazillions of applications. The only one I knew about when I did the work was clocks, and then atom interferometers, but it all followed afterwards.
Anyhow, we can look into towards varying the nanostructures or microstructure or grain refinement at nanoscale.
Well,
This.
no, it's used atoms as, equivalent of some condensed matter thing. It doesn't mimic the real condensed matter. That the real condensed matter people say this is a toy system, and it is a toy system. And in order to really test things that the condensed matter people, you got to get really colder than the atoms are. The atoms are nanokelvin. They got to be femtokelvin. But that's another thing. You can get, in special cases, down to very cold temperatures.
Thank you, sir.
Thank you. Please.
Hi, Professor Chu. I'm Mitradeep from India. It's a very nice talk. So I just wanted to know that since you worked on a lot of problems from a lot of fields, how to decide when we should stick to a problem and when we should switch a problem?
That's partially pretty easy. When I have really brilliant students and postdocs and they go off and do this thing, I say to myself, it's in good hands. It's time for me to move on. When things become very fashionable, when the many pods, I started doing some of the many pods, but when they become very fashionable, there's lots of people rush in. I say, I don't want to be there anymore because now you're racing, and I don't like to race. I'd rather come out of left field, and so my inclination is to see if I can figure out something that is really untouched. And the way you get it to be untouched is you are coming from left field with different technology, new ways of making measurements, and you apply it to new areas. Again, the theme that I learned when I was a graduate student.
Thank you.
Hi, thank you for your talk. When you're observing those motor proteins using your new microscope, does the type of cargo affect the step size and the forces that they feel as they move throughout the cell?
We don't know. When you're doing experiments in live cells, you get what the cell gives you. We're going to be starting to do them in vitro as well, because there's lots of things we can then test. We discovered in the first set of experiments that for some reason, nature would maybe use one motor, they could maybe use 2, 3, and it could randomly swap between 1, 2, 3, 4, 5 motors and back. We don't know why it happens. But let's say it's one motor, there are 2 legs, and the minimum step is 8 nanometers, so cargo moves 4. So you have to see 4 nanometers. But if you have 2 motors, if 2 legs and they're independent, one moves, the others don't, then it's 2 nanometers. And that's why we need to be a fraction of a nanometer. But there are many things that the first set of experiments were suggesting to us that, if we can, go up by a couple of orders of magnitude, both in space and time, we would be able to see. But the real thing is, I think when you're a couple orders of magnitude better, 2 or 3 orders of magnitude in space and time, you're going to see something new. And we're going to look at dynein in vitro in vivo and kinesin in vivo in vitro with this very high resolution tracking. Again, new parameter space, it's higher resolution. So already we're seeing things we don't fully understand, which is no surprise. But that's really fun. We're seeing weird stuff that was underneath the time resolution and spatial resolution of our previous experiments. But it's going to be fun.
Thank you. Please.
All right. So first of all, I would like to thank Prof Chu for to bring up the carbon capture things, because I feel so lost when always surround with all the biology things with the chemical engineering background. So I actually have a question. It's more do you think direct air capture is more like a greenwash? Because people will talk about maybe the cost is too high, it's not really effective. So how do you think about this kind of the statement?
Well, this method I described will work with direct air capture. it's hard for me to make I can make a guesstimate of how much it would cost. Right now, it costs about $500 a ton, which is ridiculous. No one's ever going to pay for that. But you're going to have to capture 10 gigatons or 20 gigatons a year. So that's, to do the math, 10 times 10 to the 10 tons, $500 a ton. This is some fraction of the GDP. So you need to, even if it's down by an order of magnitude $50 a ton, it's expensive, but it's conceivable that society will pay for that. I'm guessing that it will be of that order, $50 a ton for air capture.
All right. So can I have a follow-up question? It's like, so what do you think, like, what kind of the, maybe like a driving force that can, allow more people to, to proceed with using a direct air capture? Is it like, maybe the government have to strengthen the carbon tax, or, yeah, do you have any idea?
Well, if you had a carbon tax of $100 a ton, $50 a ton, you make a lot of money. And so Europe has pricing carbon markets that are roughly 100 euros a ton already. So there's general belief if you get to the $50 range, it will be deployed at scale. Because the scale you need, you saw that big thing. If you use the enzyme carbonic anhydrase, everything shrinks by an order of magnitude or 2. So it becomes very compact. The energy goes away. And so I'm sort of floating on cloud 9 at the moment, trying to figure out, what am I doing wrong? It's been alive for a year. The people at Breakthrough Energy Ventures are looking at it very closely to see if we've made a mistake. Whether it's flue gas capture or not, it depends on a few other things. But the air capture, I think, in my mind, looks pretty feasible. And we will need air capture. And we'll need it less than $100 a ton before it's deployed. And so if this works, it's probably the most important work I've done in my career.
Thank you so much.
Okay, last question. Thank you.
Hi, thank you for the great talk. As somebody who's been in both of the science and the policy world, what would your advice be to young scientists in communicating with policymakers?
You have to be patient. You have to try not to use jargon of any kind. And above all, you're not talking down to them. You have to convey that. Many of these policymakers are intelligent people. They're not technical people. And there's still a lot of them in the US government, for example, that still want to do the right thing. There's others who don't, but that's okay too. But so you find the good ones, and you because I think climate change is here. It's real. We're going to be slowed down in the next 4 years, but it's okay. You just make good technical progress and make it really inexpensive. The secret, by the way, of anything to transition to a more sustainable future, no carbon emission, is make it better than the alternative. And when you make it better than the alternative, people will switch because it's just better. You don't need to subsidize it. And so the end goal is always to just make it better.
Thank you.
Okay, I think it's time to close the session. So thank you very much,
Okay.
Professor
Thank
Chu.
you.